sometimes it's just nice to walk through your notes again. So this is like the notes review for chapter 7. Some of this stuff, now that you're where you are in the chapter, when you look back, you should just say, wow, this was not as hard as I thought it was at the time. So just, you probably do know all the parts of the reaction now. The reactants are on the left side, the products are on the right. The arrow means yield. The little numbers that might be in front are coefficients. And we always use plus signs. We don't use minuses in reactions. And we do have phases. S is for solid, G is for gas, L is for liquid, AQ is for aqueous, and that means that it was dissolved in water. Theory of conservation of mass. So the number of atoms on the left will be the same as the ones on the right. So that means that if the number of atoms are the same on each side, also the mass of each side is the same. They're just combined differently. Just a quick reminder, you've seen it a few times. The pink section on the chart right there, those two, those are your liquids. The gases are marked and with orange, and then the solids are green. Don't forget about the diatomic elements. They form a 7 on the chart, N2O2, F2, Cl2, Br2, and I2, as well as H2. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Remember, when they are by themselves, they're in pairs, but if they're combined with different atoms, they could be any kind of number other than 2. This is just when they're alone. And these words, when you see the word hydrogen gas, that means H2, because it's hydrogen by itself. And then oxygen gas, again, H2. And then water as a gas would be a G. These are balanced. You've done a lot of practicing with balancing. Again, butane gas, and there's the formula with the little G afterwards, plus oxygen gas will produce carbon dioxide gas and water. And the oxygen is again diatomic. And then aluminum metal is placed on a surface of liquid bromine. So again, there's your liquid. And a reaction occurs that yields aluminum bromide salt. So when it says it makes a salt like that, that means that it's a solid. And notice that phrasing aluminum metal, it's not saying that it's a solid specifically, but that's what that means. Anytime it says like iron metal or copper metal, that also is another way to say for the metals, solids. We talked through this method, and I suggest only using this for a short period of time. You want to get pretty good and get this back and forth method. These are best practiced, not just watching someone else do it. It's the best thing for you to do it. And I had a little hint on the combustion reactions. If you start going back and forth and on the combustions here, if you end up feeling like you just keep cycling around the equation, erase everything and put a 2 in front there. These didn't need it, but that's my suggestion, is to put a 2 in front right there. Now, these were more practice problems for balancing. You'll notice that a lot of times what I'll do is I'll look for something that is not 1, basically is what I'm looking for, something that's not 1, and then I check it, and then I check it, and we have the answer. I'm going to keep on going. This problem right here was one of those ones that needed a 2 in front of the problem. So if you worked it out one way, you would have wanted to go back and erase all the parts and then put a 2 in front. Also read this, write the balance reaction for copper metal. Again, that means solid copper. Reacts with oxygen gas, that's O2 gas, to produce solid copper 1 oxide. So it's copper 1, and I know oxygen is minus 2, and that's why there's a 2 down there. So these are our classifying of chemical reactions. We went through a few different types. We're just going to look at the pictures and review. So single displacement is where you'll notice the purple. There's a single element wherever there's a purple in this section right here. There's a single element on the left and then a single element on the right. It's where only it's the negative part mixes and joins with the element, and it leaves the other piece behind as an element. And then anytime that all the species present are some kind of a positive and a negative Anytime that you've got all of those, it's going to be double displacement, and it's where like the insides and the outsides join up, or you can say that these two switch places. That's a double displacement. Synthesis only makes one thing. Notice in the purple, and I don't mean one atom, I mean one type of product is the only thing that's made. So you can have 8 of them or whatever, but there's still just one type of product. And then over to the right, decomposition is in contrast. You've only got one type of reactant. And then for combustion, it's going to be like hydrocarbons or stuff with carbons, oxygens, and hydrogens reacting with water, and it's making the CO2 and water. I'm sorry, it's reacting with oxygen, making CO2 and water. And those are combustions. Now we went back and we mentioned that there are some subcategories of a double displacement. So precipitation is the word that means solid. And so in this purpley double displacement category, when we had a solid, that was precipitation. This is also a precipitation reaction. Oops, I'm in the single displacement. Just one second. So in the double displacement, when you make a solid, you have a precipitation. And when you make a solid, you have a precipitation. And then an acid base is where you have something that has an H on the front and an OH in the back. And they make water. That's the acid base. Now this is where we talked about how to go about making products. So I left in these cases, I left the positive thing in place. And like you switched where the negative thing was, or you can leave the negative thing in place and switch where the positive thing is. But this was a single displacement. Again, you have an element and an element. And this was a double displacement. By the way, there's a H and an OH, so its subcategory is acid base. This one right here is a double displacement. This is a single displacement, and this is a double displacement. And by the way, this isn't stated, but this is a solid, so this subcategory would be precipitation. And I bring all that up just to point out that the ones that you can predict products are singles and doubles. And then as well, you can also predict products for combustions because it's always waters and gases. Now this section was just like a little bit of a preview. We're about to be heading towards enthalpy and entropy in Gen Chem 2. So don't overly focus on that. Most general chemistry reactions are in water. The word precipitate means solid particles. Ironically, we use an S for them, but it means insoluble. Whereas for the soluble stuff, which also has an S, we use AQ. And then we talked about how if it's soluble in water, you can see there's the water stuck together and it has a dipole. We talked about that in chapter 4. And so when it dissolves in the water kind of holds it steady while it's being separated because the water has just a little positive and just a little negative holding it steady. We also talked about if you have a little bit of something on the bottom, that means there's some solid on the bottom that couldn't dissolve. It was like it ran out of space. Nothing more would dissolve. And that's the insoluble and that's the solid. You can make a gas. Gases can be soluble in water, but generally you'll also see them bubbling out of the water. So what happens to a sealed container if you're doing a reaction that produces so much gas it won't dissolve? It will break the container. So then we walked through some ideas. There's a few ways that you know if a reaction has happened. It's if you form a solid, or if you form water, or if you make a gas. Anything, if you make something that stays stuck together on that right-hand side, it means the reaction is likely to go. And we call it, at this point in chemistry, we say it is a reaction. What we also can say is that there's no reaction if you have none of those. And we had our list of strong acids and our list of strong bases right here. I also mentioned that this will turn into a gas and this will turn into a gas, and it turns into gas and water. This one is CO2 and water. This is SO2 and water. This is NH3 and water. We also mentioned that oxidation reduction reactions, there are electron exchanges. We're skipping that topic this semester. Then we had the solubility chart and talked about how you want to always start at the top and you look for like one of these ions first before you look for anything else. And then you work your way down the chart for every part of the reaction. And we have some examples here if you want to go back and review or practice being able to figure out solubility. You can. This is not going to be on our test this semester. You will be told the solubility. So this is showing how you can turn things into complete ionics and net ionic equations. Sometimes this is also called a full ionic equation. And you just show that anytime it's AQ, it breaks into its two parts. AQ breaks, but solids stay stuck together. Don't forget that if you have a little 2 here, it pops into the front because we already showed the picture. Here's your copper chloride over here. So in water, it breaks apart into the charged species, Cu plus 2 and 2 Cl minuses. So that's true. Again, the 2, it applies to not just the Ag, but also the NO3. And this little 2, again, it gets thrown in the front. That's the biggest tricky part. Don't forget to include all your phases. It looks like on this one I left out AQ and AQ right there. Then the spectator ions are the ones that you cross out. That's Cu and the NO2. It's when they have something on both sides. And then you end up with your net ionic. So as long as you have a net ionic, we say the reaction's going to go. But if everything cancels out like here, then it's no reaction, and everything is a spectator. Make sure you balance them ahead of time. But these are just lots more examples. Notice here's our solid in that case. And I also did this thing where I mentioned like doing these vertical lines as you go along to remind yourself to break those ones. And then, when it has a solid like this, water makes a liquid. When you make liquid water, it stays stuck together. And then we've got the vertical lines for everything else. We got more examples here. Make sure you feel really confident about those examples. And then this was kind of one of those all-everything reviews. If you want to go back and, try a few more of these if you need to, you can. But you're predicting the products, you balance the reactions, you put the phases in, and then after all of that, you break it into positives and negatives to figure out if there's a reaction. And these colors on the side are for the ones that did have reactions. So look, if you have like AQ for everything, AQ, 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 that means everything breaks apart, and that also means everything will cancel. Again, AQ, 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 everything will break apart, so that's no reaction because everything cancels. But everything else, so like see right here, we have a solid. So that one's going to have something. This is a solid. And then let's see, this is a solid. This is a solid. And this bottom one is no reaction. So the ones that broke up further and they needed nets, I color coded them and put them down here. We skipped this section this semester. And this is the last bit where we were talking about how you can use those coefficients you've been balancing with to get between different parts of the reaction. And so you can go from a mole of one thing, and this is what's different from every other point in the semester. You can get from one part of a reaction to the other part when they both are in moles. We already talked about how you can use Avogadro's number to get to particles, or you can use molar mass off the chart to get to mass, or you can use molarity to get to the volume. We've already talked about that, but in all those cases, notice it's all purple. Those were the purple square. They were all the same, and same with the blue square. It was all the same. What was different at this point in the semester is now you know that you can go between the purple and the blue square. So this is again talking about how you can take these front coefficients and you can relate them to each other. Here's our first examples of doing this, and then it gets a little more complicated further on. we'll go ahead and just look at this one right here. This is a reminder of how to use that Avogadro's number. So you can take your 3 grams right here in green, you turn it into moles of hydrogen, and then right here we've got 2 hydrogens to 1 oxygen, and that's because of these coefficients. And then don't forget, Avogadro will take us from moles into molecules of O2. But most of the time, you're not trying to get to molecules. Most of the time, you're trying to get to a gram amount of a product. So the look of this is very, very common. And you'll be given information like 10 grams of oxygen. So there's your 10 grams. This is from the periodic chart. These are from the reaction, your 2, and then the understood 1. And then this is from the periodic chart. And you're just trying to get those units to cancel. So cancel, cancel. Cancel, 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 cancel. And you want to double check for sig figs all the time. So it's almost always that front number gives you your sig figs. Don't include these for your sig fig count. And our periodic chart numbers usually go to 2 decimal places. The chart that we have is 2 decimal places. So all of your periodic chart numbers should be, almost all of them will be 4 sig figs, except the very, very tiniest of elements. This was explaining the ideas of limiting and excess reagent, and it just showed that I'm going to look at this one we're going to look at this one down here. And we used circles to be O's, and the C's were squares. And so we had a total of 4 COs, so you can see square circles on these. And then we have 6 of the pairs of O's. And then we want to know how many CO2s can you make. So you've got the squares, and you put those out first, and then you start putting on your oxygens, and you'll notice you have a lot left over. That means that your carbon is what limited your reaction. Or in this case, because this is the molecule with the carbon, your CO is what limited the reaction. There was tons of oxygen. Most likely that's because carbon monoxide is not safe to breathe in, and oxygen is really easy to breathe in. When you're doing this math-wise, the key part to this is that you are given a reactant amount for both reactants. So this was 10.0 and this one was 32.0. So you had a number for each of those, so you can't guarantee that they're both going to be used up. The way you work these problems is you want to write this part and this part down first before you start setting up the train tracks so you don't forget. And then grams to grams, moles to moles, and then, moles to moles, and then into grams. And then we've got, again, grams of oxygen to grams of oxygen, moles to moles, moles to moles. So these coefficients right here are coming from the problem. These two, you've got it like right here and right here. And then these two are also coming from the problem. It's this guy and this guy. I'm going to erase those colors though because I like the colors that we originally had. So that is how you figure out amounts for your product. Now the key thing is you're going to get 2 numbers. It's for the same product. You always cross out the big number and then square up or make a big note so that you know that that's your real number. Immediately go over and say this is your limiting reactant and this is your excess. So you have it all labeled. As a note, you may also want to label this as your theoretical yield. And then if you need to know something about excess limiting reagent, you're going to need another train track. And you take your limiting, so that's this one right here, and you start another one with him, but this time you're converting it into your excess. So this was your limiting, and you're converting it into your excess. And then you figure out how much O2 is used. Now that's not really the answer. They want to know how much was left over. So you want to go to the problem and see, I started with 32 grams of oxygen. So here's what I started with. So I had this much, I used this much, and then that's how I know how much is left over. And when you're doing significant figure subtraction, you go to the farthest out decimal place. So this is a tenth like the other two. So we have plenty more of these if you need more practice. There's a little comment about percent yield. So percent yield is this theoretical. That's what all of these are calculating. The one that's left over, these are all theoretical. They're perfect. They're calculations only. In real life, you don't really get them, but you want to get close to them. So the way you know it's that kind of a problem is I'm going to look at this one right here. So when I'm putting these gram amounts below, notice before I had a number here and a number here, but now I don't. Now I have a number here and I have a product number. You read the problem really carefully. This is what they made in the lab, or they handled it, something like that. So that's great. This is going to be your actual amount. So on the left, this is how much that you had. And I'm sorry. So on this left side, this is how much aluminum that they have you start with. And you want to go from grams of aluminum into moles of aluminum into moles of the product. So this is that same product. This is our theoretical yield right here. And so the reaction theoretical goes on bottom. Actual, that was what was stated in the problem that we haven't used at this point. It's this number right here. It hadn't been used yet. It's the one that was placed here. That goes on top in the theoretical. And your number should always be less than 100%. You can't make more than you're predicting. If you have a number more than 100%, then it means it's still wet or you made an error. It means that it's not possible and you made a mistake somewhere. And then the last little bit in this chapter was this quantitative chemical analysis, and this is basically saying the same style of thing, but now we're doing molarity. So we have a problem. It's kind of hard to see it right here, but here's our problem, and here's the information that was given in the problem. You were given a milliliters of one, and you are welcome to convert that to liters. And then you were given a milliliter and a molarity. Don't forget. Cross out molarity and make it moles per liter. Don't forget that that is 2 units, not 1. So the way you know which one that you're starting with is that you're starting with the one that isn't the one you want to end with. So this right here is asking us to end with HCl. We want that to be the end. So we want to start with the NaOH. And then we just take the thing that has 1 unit. And this one right here is what has 1 unit. And here we're turning our molarity, our milliliters into liters. And then our liters into moles, and then our moles into moles of HCl. When we do that, that gives us how many moles of that gives us how many moles of HCl we have. We are not done because they are asking for the molarity. So that's when we use our green number over there, the one that we hadn't used yet. Make sure you're putting it in as a liter, and you end up with molarity of HCl. That's how you work these problems. You can have problems like this that are full limiting reactant problems also. Make sure that you balance them correctly. This first example is 1 to 1 to 1 to 1. This second example is 1 to 2, 1 to 2. Make sure you have that accounted for. And then these last few problems, here's an example of how you, again, don't forget you can turn something into molecules. You can use moles and get into molecules. And also this reminder how to get from molecules to atoms. That's from the very first test. Just reminding everyone. Then we had more example problems. If you want to come back and look through how to practice these, you totally can. That's the review for Chapter 7's notes.